Welcome to what should be our final video of the year. The topic we're covering today is solving exponential equations using logarithms. If you remember right, we solved some exponential equations the other day, things that looked like this. And our technique for solving these was rewriting both of those as 2 to the third and 2, and basically getting the same bases. Once we got the bases the same, we set the two exponents equal to each other. However, that doesn't really give us an ample way to answer something like this. There is some power out there that I would raise 2 in order to get 17, but I don't know what it is, and it's not going to be an integer. It's going to be some decimally kind of number that is much harder. We wouldn't be able to solve it using the other method because we can't rewrite these both to a base of 2. So, the kind of equation we're going to deal with today is something that looks kind of like this. 3 to the x equals 29. I know roughly how big this should be because I know 3 to the third is 27, not quite big enough. 3 to the fourth is 81, which is too big. So I know it's going to wind up being an exponent between a 3 and a 4. Before I can show you how to solve this using logarithms, I'm going to state one of the properties of logs so that I would have approached much more gradually if we had had more time left this year. I would have developed where they came from and why they work, and we would have practiced with the particular properties of logs. So what I'm going to do is cheat. I'm going to tell you one of the properties of logs. The log to any base of a quantity to a power is equal to the power times the log to that base of the quantity, of the argument. What this is basically saying is when you have the log to some base of a quantity to a power, you can bring the power down front as a multiplier. Well, that's handy because if you remember right, the variable we're hunting for is up in an exponent. And by using that property, we can get that variable out of the exponent and down at a level where we know how to handle it better. So, that's what we're going to do. We're going to use this property that lets us bring the power down front as a multiplier. Now, I'm allowed to take the log of two equal quantities. I'm able to take the log of both sides, so long as I'm choosing the same base. So I could take the log to base 3 of both sides, I could take the log to base 17 of both sides, I could take the log to base 10 of both sides, or the log to base e of both sides. It doesn't matter. But I think, just so I don't have to write as many subscripts, I think I'm going to go with log to base 10, because we have the advantage of having a key on our calculators that can actually find the number. So, I'm going to take the log of this side of the equation and set it equal to the log of this side of the equation. Remember, this means base 10, right? So whatever power I raise 10 to get this should be the same as if I raise the log to base 10 of this, because these two amounts are the same. The equal sign says so. So I took the log of both sides, and now I'm going to use this property right here. I'm going to bring this exponent down front. By the way, if this exponent had had multiple terms, I should have put it in parentheses so I would be able to remember that it's a binomial. Well, this one ended up being just a single little x, and that's fine. Keep in mind what we're trying to do. We're trying to find x. Remember that the log to base 10 of 3 is just a number. It's a number that when we raise 10 to that power, it lands on 3. It's even smaller than 1 because 10 to the first would be 10, and 3 is much smaller. But it's known by your calculator. So this is really just an ugly number. So if I had like 5x equals stuff, I just divide by 5 on both sides to get the x alone. Well, that's what we're going to do here. This is just a number. So I'm going to divide by log 3 on both sides of the equation. Now I should make another point. If this were log 30 over log 3, I could not do some reducing with the 30 and the 3. You see, log 3 is a whole symbol unto itself. It's a particular number. This belongs to this. So you can't go and take the arguments and start doing arithmetic with them. They belong to the word log. So x is equal to log of 29 over log of 3. So at this stage, if you were trying to solve this, you would go get a calculator. I'm going to use a calculator right here. And you can either get any scientific calculator, any calculator that has log or ln on it. You can even turn your cell phone sideways if you have an iPhone when you're in the calculator app. But I'm literally going to go log, and they're usually on the side here, log, and 29. Sometimes it opens a parentheses for you. Sometimes it opens up a parentheses for you. Sometimes it makes a box. But I've got to close a parentheses around that so that it knows what it's taking the log. So you would have to advance out of the box if you were doing that with your calculator. And then divided by log 3. I press log 3. I close my parentheses. This is what it looks like on my calculator screen. And then I press enter. And it gives me a rather yucky number. See, I told you it'd be between 3 and 4. If I wanted to check and see if I was right, what I could do is I could store the number in A, which is alpha A, enter, and then I could actually try it out on the problem. 3 raised to the alpha A, and I press enter, and boom, it lands on 29. So I've tested my value. That's not part of the process I'm requiring you to do, but it's comforting to know that you can actually see if these numbers work, especially on these more basically written problems. It's not that hard to check. Okay. So I'm going to put my calculator here off to the side, and we're going to try another problem. Take a screenshot of this if you want to. The home and power key together. And now I'm going to erase this. Certainly another way to have an image of this other than taking a screenshot is to put it in your notes that you're hopefully taking on any of these videos that we do. Okay, so now let's take a look at the second problem. 3 times 4 to the 3x plus 2 equals 78. Okay, so it's kind of ugly. This one is clearly much more complicated than the other. It's got a more complicated exponent. There's a 3 here multiplying the 4 to the power, and that 78 is not a particularly friendly number. All right, so if you remember right, all the ones we've done had just a base to a power. This 3 is keeping the base to a power from being alone. So the first step would always be to isolate the quantity that's being raised to a power. So we'll divide by 3 on both sides. 4 to the 3x plus 2 is equal to, and 3 goes in there, actually that goes in evenly. 3 goes into 7 twice with 1 remaining, and then 18. 3 goes in there 6 times, so that actually came out to a nice tidy little 26. Now we've got the base and its power isolated. Now we take the log of both sides. So I take the log over here. I'm not worried about having to come up with difficult numbers. My calculator can do all the heavy lifting. But if I take the log over here, whatever type of base you use over here, you have to use the same base over here. I'm using base 10 for 2 reasons. Again, so I don't have to keep on writing the bases, and because I know I have a calculator key that can solve those type. Now we have the log of something to a power. According to the rule, when I have a power up here, I can bring it down front as a multiplier. So I'm going to bring this whole thing down front. Do you see how that's 2 terms? I'm going to have to put it in parentheses to remind myself that it's a binomial. We're almost done. Some people distribute this through and then bring the second term that results over there. But I don't see any problem with dividing by log 4 on both sides to begin with. So I'm going to divide by log 4. Remember, log 4 is just a number unknown to us, but it's that power that we raised 10 to land right on 4, ugly as it is. So the calculator knows what that number is, but now this is gone, and I've got 3x plus 2. 3x plus 2 is equal to this mess. How do we get x alone? We subtract 2 from both sides. I'm going to run off the bottom of my whiteboard, so I think I'll just write the minus 2 over here. And then I'll divide both sides by 3. Now this is a mess, but we can clean that up with a calculator. So, I'm walking you through the steps with the calculator. I'm going to go, and what I'm doing is this result. I'm going to go log 26. I know you can't see my screen, but at least you can see the buttons I'm pushing perhaps. I'll get a little closer. Log 26. I close my parentheses, or I advance with a sideways arrow out of the box that it created. And then I go divided by log 4. Close my parentheses again around the 4. So those parentheses or box that it opens up, it's waiting for the argument. So you take this argument and you put it in there. Now I'm going to press enter. And I get a 2.35-ish kind of number. I'm not going to take the number out of there. I'm going to go right ahead to subtracting 2. I'll press enter again. That's like figuring out what the top of that fraction is. Then I'm going to go divide it by 3. Enter. And my final answer was 0.1167-ish. That is a number that would work in the original equation. So the number came out to be, I'll write it over here because I run out of room, x ended up equaling 0.11673999. Nope, just 2 9s, 53. So 0.1167399953. And I would be slow to do any rounding. I think it depends. If you're doing a word problem and you know how to interpret it, you'll know how safe it is to round. But since these are exponents, they make a huge difference to the outcome. I would not round them, at least in the beginning. Any questions? Let's try another one. Anyone screenshot? Here's your chance. All right, it goes away. The problem with me giving you this information in this form is it sometimes makes for a longer video. But the benefit is it's still about half the time I used to spend in the class. So let's try 2 to the 3x minus 1. This is example 3. 2 to the 3x minus 1 is equal to 5 to the x. Now we have 2 exponents that contain the x, and we need to get those x's out of both of those tops. So to begin with, what we're going to do is we're going to take the log of both sides. See, the bases with their powers are already isolated. There's no 3 times this, there's no plus 4 sitting on the ground here, so I'm just going to go ahead and write log and log. Now I'm going to use that property and bring the 3x minus 1 down front. Keep in mind, I cannot write it like this because the order of operations will do subtraction rather than multiplying both terms by that. So we need parentheses around there to say the log 2 is multiplied by the whole thing. Over here, I took the log of this, the x comes down front. And just so you know, there can be slight variations into the order that people do things in. I think what I'll do this time, just to show you it can be done this way, is this is just a number. This is like a 7. If I took a 7 and distributed it to both terms, that's a legal thing to do. I'm going to take the log 2 and distribute it to both terms. 3x log 2 minus, and then log 2 times that. Over here we have the x log 5. Okay, how many terms do I have? I have one big long string of multiplication, another, and another. So we've got 3 terms, and this is the separator between these 2 terms. So I've got 3 terms. How many of them involve the x that I'm trying to solve for? This one has an x in it, and this one has an x in it. So let's get all of our terms that have x in it to one side. I'm going to bring this over to here, same way I would in algebra. I just add its opposite signed thing. And now I have here 3x log 2, log of 2, minus x log 5, minus log 2, equals, and this is now all gone, so it's a 0. I have all the x terms on one side. There, here's an x term and here's an x. This term, however, has no x. So I'm going to bring that over to the other side. 3x log 2 minus x log 5 is equal to, and when I bring that over, I'm really adding log 2 to both sides. So you can see this one was a little more complicated because we ended up with more than one x term. We're almost home. If this were like a 5x minus 2x, we'd be combining like terms. The presence of all this other stuff makes it a little bit less likely I'm going to be able to do that. So you know what? I'm trying to get x alone. I'm going to factor out both of these terms have an x multiplier. So I'm going to bring out the x. So I'm just taking the x out of both terms. See how there's a common factor out front? That times that gives me this term. That times that gives me the other term. Do you see where we're going with this? I want to get x by itself. Right now it's being multiplied by this stuff that doesn't involve any x. So I'm going to divide by this on both sides. So 3 log 2 minus log 5. 3 log 2 minus log 5. So we've gotten rid of this by dividing by this on both sides. You see how I'm crossing them out so that you can still read what's underneath? If you're trying to show me the work that you're doing and the process that you used to get there, you should always cancel out lightly. That way you can also go check your work and see what the original work was. So x, this is all gone, x equals the result of that calculation. It's not as crazy as you think. We're basically going to put it right into our calculator. One caveat, you've got to put parentheses around the bottom, because otherwise when you go divided by the first thing, it's going to do the division before it ever gets to the minus log 5. So, let me clear and I'll get close here. So hopefully you can see both. I'm going to go log 2. And then I'm going to go divided by, and then parentheses, 3 log 2 minus log 5, close parentheses. You see how that looks? And this can be done on any scientific calculator. So now I just push enter, and you should get a number like 0.7659-ish. I'll write the number on the board. I'll write it up here. So this number is 0.7659. That was a good year. 107,322. So with that very complicated first equation, which we had 2 to the 3x minus 1 equals 5 to the x. We took the log of both sides. Using that property of logs, we brought the powers down front. We then distributed the log 2 to both terms. And then we got all the x terms on one side and all the terms without x on the other side. Because these weren't technically like terms, we actually factored out the x. Here's what the stuff inside the parentheses was, and that became what we divided by on the final step. That is just about as difficult as they get. We have one more problem to do that's a little bit different looking. You might be able to guess what it is. You want to take a screenshot of this? Okay, here it goes. If ever I offer a screenshot and you take a moment to grab your calculator, your iPad, in order to take a screenshot, you can always pause the video and then restart it. Okay, so here is the last problem. E to the 5x plus 1 equals 271. One of the videos that I'll put up later just for your benefit is to show you where E comes from. But for now, just note it's approximately this big. It's like pi in that it never ends and never repeats. So we use the symbol as a convenience. Well, with this kind of an equation, I can certainly take the log to base 10 on both sides. My calculator will be able to handle that. But why don't I take the log to the base of v on both sides? ln. Remember, that's really a logarithm. It just is written as a natural log to distinguish it from the common log. They don't usually write the base, but do you remember what the base is? It's E. The calculator knows that. But I want to bring to your mind some problems we had done earlier, a session or two ago. Do you remember when I asked you what is the log of 3 to the 20th? What power do I raise 3 to if I want to get 3 to the 20th? And it came out to the exponent every time, so long as these matched. 3 to some mystery power equals 3 to the 20th. Well, that must equal 20. Well, that's really what we have here. What power do I raise e to if I want to get e to the 5x plus 1? Well, I raise e to that power if I want it to look like this thing. And over here, I just write ln 271. Basically, if I take 2.718-ish and raise it to some mystery power, it can land right on this number. I don't know that number. Your calculator knows that number. Don't worry about it. So now I want to get x alone. That's what I'm really looking for. I'm going to bring the 1 over there. I'm going to go minus 1 to both sides. Now be careful. 5x is equal to the natural log of 271 minus 1. Don't think you should subtract 1 from this number. Remember this, they're married together. Till you take the log or rewrite in exponential form, this belongs to this, and the whole symbol means something. So you're never allowed to play arithmetic with the argument and some other term that adds or subtracts or multiplies or divides. So it's going to stay just like that. Now how do I get x alone? Divide by 5. So x is equal to natural log of 271 minus 1 all over 5. So let me now grab my calculator and figure out what this number is. So natural log of 271, that's when you make sure to hit the ln key. So ln 271. Notice it opened parentheses or it opened up a little box, so you've got to close it so it doesn't take the log of 271 minus 1. Right, minus 1. There we go, and then let's hit enter. That's the result of the whole top. Now go divided by 5. Enter. And there is your mystery number, 0.9204-ish. There you go. We have found the mystery value, and you now have everything you need to know to solve logarithmic equations. There are a few shortcuts you can use with certain types of equations structured certain ways, but we won't get to them, and I might include that in a future video. So I hope this video was helpful.